Okay, so welcome everyone. We're gonna start today. So okay, so let me go over the uh, 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 like what we're gonna cover today. So I think last time we were discussing about various NLP techniques at the beginning, and then towards the end we were talking about word embeddings in general. We weren't able to discuss word to vec last time, but we're going to discuss that in a little bit more detail to get a sense of why we'll get embeddings which are similar to each other. And in the meantime, so today we're going to look at a slightly different set of techniques. They're also, of course, useful for natural language processing. So that's the continuation with that. So I'll talk about the goals of today's lecture when we get there. Okay. So okay, so let me just quickly recap, restart from a little bit earlier point. Okay. So recall what our objective was last time. So our objective was to learn an embedding. Right, and we denoted the embedding by the letter W, or you can think of that as a function as well, because it's a linear transformation you'll see, and so it can be represented by a matrix. So so basically this W is, if you think of it as a matrix, then it is of size V times, last time we chose this number 300. It just means that, so where V is just going to be the size of the vocab. Okay, so basically we need a linear transformation, or basically this matrix where each row corresponds to a vector. And of course, the vector size is 300 dimensions. And there's a vector corresponding to every word in your vocabulary. And we want to get a really good representation for W, which captures some sort of a semantic meaning, which was not possible before when you were just using, for example, a one-hot encoding of the words. Okay, if you use one-hot encoding of the words, your word, the W matrix would look like V cross V, because if the word is cat, there'll be a cat, one for the cat word, and everything else 0. If it's a dog, let's say the next word is dog, then there'll be one for that, and everything else 0. So this is one-hot encoding of the words, right? But here the vector length is capital V, which could be, let's say, 50,000, right? Yeah. So this is what we discussed last time. So our goal was to learn an embedding. Embedding just means a representation, and we talked about what we did the previous lecture when we were talking about the image embeddings, which were just the activations of the penultimate, let's say, fully connected layer in BGG 16 or 19, one of these networks, right? So an embedding is just representation, and we want good representations of words so that we can do the various tasks we discussed last time, including sentiment analysis, or machine translation, and various other things. Okay, and we're going to talk about a little bit more on things like machine translation today. Okay. Now, yeah.
Why is that dimension 50,000 by 50,000?
It's just the size of your vocabulary. So different vocabulary. So depends on which language you want to model and how much you want to model. For example, let's say you're doing Twitter sentiment analysis. On Twitter, of course, there's going to be a different set of symbols or words used. Maybe it's not the full English language, but at the same time, it may have additional, symbols, right? So I just said 50,000 is the size of this particular language, but what is the size of your language?
But one dimension should be the number of examples, right? Even in one hot encoding?
No. So this has nothing to do with the data set at all or examples. This is just a this mapping. So W takes as an input a word, let's say cat, and produces a vector. So we want to learn this, of course, and for that we'll need data set, and that data set will have examples. But
Okay.
if you take that as an input, there has to be a 300 dimensional, let's say in this example, 300 cross 1 dimensional vector that represents the cat. Okay.
Okay. Yep. Thank you.
Um, okay, so last time I discussed an example task to learn such a W, which was that, okay, so let's say there's that W which can take a word and produce a vector. Let's say, and so I was going to, last time I created an example task to see if we can learn a W, and I did not really specify the details of the task in enough detail, which was that the task was about classification. So I had 5 words. So word 1, word 2, word 3, word 4, and word 5. And and this sequence, I would say, is a valid sequence if it came from a valid sentence, let's say in Wikipedia. And if the sequence was not in these types of valid sequence of words, then I would just call it invalid. So this was the label. And this was the these 5 words were the inputs. Okay, now words in themselves are input doesn't make sense, so we would apply the W transformation that we have, this guy, on each of the words, right? 5 times, let's say, and they'll get 5 vectors, right? V1 to V5. Okay, once we get these 5 vectors, you can just think of it as, you can append them one below the other, or you can add them up. Essentially you have a vector representation of your input. The moment you have a vector representation, you know how to do a classification task. Right? You can just, for example, use logistic regression. You have some dimensional input vector, and you have binary labels, valid or not valid. You can just assign zeros and ones to these labels, and then just do classification. Okay. So that's the classifier here. And we were saying that, okay, why did we create this auxiliary task? Was to hope that maybe we can learn W when we are doing this whole, when we are trying to improve our classification performance. Okay. So of course, the classifier itself will have parameters, let's say theta. W itself is, has a bunch of parameters, because the W matrix, we want to learn the entries of the W matrix. All these entries are essentially parameters that we want to learn, the word embeddings. Okay. So let me just call it phi, all these parameters. Let me call these parameters theta, the parameters of the classifier. I'll just try to learn phi and theta by trying to minimize loss, like binary cross entropy loss, okay, or what we discussed as softmax loss. Okay, so this was the higher level idea. We're going to make this very, very concrete today in a couple of minutes when we're going to talk about word to vec. Which, what is this, what is the specialization here? All I'm saying is word to vec specifically says what exactly is the task, what is the input and output training data, and pretty much that it. And using that, we can understand why the word embeddings are going to capture some semantic meaning. And that was I think the question that we left out last time. I think it's written somewhere. Yeah, so why do we get similar vectors? Okay. So let me go back above. So here what we did was actually just describe a high level task and hope that if we minimize the parameters of the classifier as well as the W matrix entries, then we'll have a good embedding. And then the next few slides were talking about if we had a good embedding. So let's say we had an embedding, then how do we think about whether it's good or not, and so on. And that's where I guess that's where we started over here. And we said, okay, just to understand whether it's a good embedding or not, what you have is for every word, W1 all the way to how many ever words are there in your vocabulary, let's say 50,000. For each one, you have learned a vector, right? V1 all the way to V50,000. And you can always project them back into 2 dimensions to just get a sense of whether the words are embedded. So the word or these V vectors make sense. Okay, and because of course we cannot really visualize these V vectors themselves, but you can do a few things, right? For example, even in this, let's say 300 dimensional space, because each of these vectors is in 300 dimensions, you can pick a word and try to find its nearest neighbor. Of course, although it's in a 300-dimensional space, we're trying to find nearest neighbors. As long as the cursive dimensionality doesn't, really mess up things, you will see that the nearest neighbors vectors, and therefore their corresponding words would be semantically closer to the word of interest. Okay, so you could do a nearest neighbors, but here in this slide we are trying to show what if you did just projection. Okay, so and one projection operation or one projection function um, you can use is TSNE. So I think it's called stochastic neighborhood embedding. I think, but it's just a procedure to a nonlinear procedure, very similar to PCA, to reduce dimensions from 300 to in this case 2. Okay, and so that reduction was done for, and when in this example actually we did the reduction from these references are from word to vec, but that is not critical here. Let's say we have an embedding, we can always project it down. You can visually inspect whether your embeddings are good or not. Let's say if you had, a Twitter data rather than regular English articles, and then you can zoom in and see whether the things are close to each other or not. And I think in this slide we have the numbers all together, and here we have the days days of the week and so on, and months in all together. Okay. So at least it gives us a sense that maybe the embeddings or these 300-dimensional vectors that we have are okay in terms of trying to capture semantic meaning. Remember, our benchmark is uh, let's say one-hot encoding vectors. They don't have any, all words are equidistant from each other. All words are similar to each other. All words are not similar to each other. Okay, so we have an improvement over that clearly. Okay, so and then you can also look at, I guess I jumped forward a little bit. We can do nearest neighbors for some words, and in this example, I guess this paper did nearest neighbors for their word embeddings to show that the word embedding is good. Okay, and yeah, so this intuition is, so why words will have similar meanings is basically that the words will appear in similar contexts. Okay, so that's, when you design an auxiliary classification task, if two words appear in similar contexts, like you'll see operates the largest medical school, and you may see operates the biggest medical school, or you'll see operates the biggest something else, maybe engineering department. Okay, so but if operates and largest, operates and biggest may give a sense that largest and biggest are semantically similar to each other. Okay, that's the intuition, but we're gonna make it a little bit more concrete when we talk about word to vec. This was a comment on data. Last time I think I went over a little bit very quickly. So we don't need to see all combinations of words. Okay, so for example, earlier in a classification task, I said look at all sequences of 5 words, W1, W2, all the way to W5, and call that as valid. You don't need to see all, permutations of these words, for example, right? All permutations of your vocabulary don't even occur in the regular language. So you don't need that to learn good embeddings. Okay, so and then the next few slides are just talking about, again, we have an embedding. Let's say we have already trained it. Let's understand, does it make sense or not? And for some embeddings, people have made sense, and this is an example of that. So for example, here this embedding was such that you could subtract the vectors, two vectors, and for example, woman minus man, the vectors corresponding to woman minus the vector corresponding to man. So the difference between is another vector, would have a very similar, the vector would be similar. So what does the two vectors being similar mean? It's just that they may have similar direction and may have similar magnitude, okay, or similar entries themselves in each of their coordinates. Okay, so there's one way to make sense of your embedding, but it's actually not a, so I'm not suggesting that this is a way to diagnose your embedding. This is just a cherry-picked example in particular from this paper, I guess. So, and similarly, some from a different paper, they're trying to show that their embedding makes sense by looking at relationships, like France is to Paris, and Rome is to what, and it's France is to Paris and Italy is to Rome, right? So they can see, like for example, they can do this operation vector 1 minus vector 2 plus vector 3 is similar to vector 4, which is the vector 4 is a semantically related word. Okay, so that's this huge table is just saying the same thing. Okay, now different examples. And now the next few slides were discussing about the uses of embedding. So first use, once you learn W, let's say you have learned W using this auxiliary task, then what can you do with it? First thing you can do is wherever you're using, for example, one-hot encoding, you can just change it to this embedding. Okay, even if so this W was learned on a particular classification task or particular auxiliary task, but that task was irrelevant. It was not your objective. Your objective was to get this embedding function or the matrix W. Once you get it, you can use it for other tasks. Okay, and this was similar to how you could use CNN's feature extractor in other tasks. Okay, like in transfer learning section that we discussed earlier. Okay, so you can use it for other tasks. And the second thing is you can also, so this is about that. And I guess this is the same thing. So in a diagram, so this is the original task where you learn W, and you can use it for a different task G. Okay. So C is the classification task, W is your embedding, and G is your second task that you want to carry out. It could be a different classification task, for example. Okay. And so that's one use of embeddings. There's actually different ways to embed as well. And the second way to embed, which is, I guess, a little bit more complex, but I just wanted to give you a sense of embedding is not just, you don't have to learn an embedding. First of all, you can use pre-trained embeddings. Second thing, if you actually have to train an embedding, you can train an embedding using an auxiliary classification task. And the third thing is it doesn't have to be a straightforward classification task. You can actually do something more complicated. And here is an example. Okay, here we are actually learning two embeddings, W English and W Chinese. Okay, so we're learning two embeddings. So each one will have its own vocabulary, right? Words. We're learning these embeddings by having not a classification task, but actually a loss function, which ensures that, okay, whatever vector you pick for a word, let's say university, and whatever vector you pick for the equivalent word in Chinese for university, those vectors are similar to each other. Maybe you can just use a squared loss. Okay, that vector similarity, some distance measure for measuring the distance between two vectors. Okay, and let's say some word pairs which are translations of each other. Okay, so that would be your training data. So university and this word here need to be you prefer that their word embeddings are the same. Then you can impose that in your loss function, and then the vectors, the embeddings that you get for English and Chinese will be aligned with each other. And the alignment is basically, if you again do that PCA or TSNE, then the yellow words in English and the green words in Chinese, if you map them into two dimensions, hopefully words that you did not use in your training, as in words that you did not know were translations of each other or are similar to each other across these two different languages, maybe they'll fall close to each other in the space. Okay, for example, this word combine and the word similar to it. Okay, maybe you did not use that in your training data, but since you aligned the word vectors by a property choice of loss function, you can visualize both the embeddings and get quick translation between words that you did not know before. Okay, so this is one way to, this is, I guess, it's called shared embeddings or bilingual word embeddings. And you can use this as a very cheap way to even do a machine translation. Okay, once you have for each word what it's for each word, go to the embedding, find its nearest neighbors, and look at the nearest neighbor, which is a Chinese word, and pick that word as the translation, right? So, and if you do that for every word in your sentence, you can get a simple, very naive, I guess, translation output. Okay. But you don't have to limit yourself to two word spaces. You can actually do, you can work with words and images and ensure that the image embeddings and word embeddings can also fall into the same space. Okay, and that you can do because you can, let's say you have um, uh, let's say you have images and their corresponding words, like classes, for example. You can ensure that those two, so the image is embedding and the word, the label corresponding to it, the word cat, let's say, it's embedding. Both are in the same, both will be mapped to a 300-dimensional space, and those vectors are similar to each other. Okay, so you can do that by changing W, or you can change this, like a deep connet as well, or you can keep it fixed, and it's fine. So basically, you're trying to ensure that the words are aligned to the images embeddings. Okay. And why would you do this? You can do that again to figure out if you see a new image, um, uh, where does it fall, and what's the appropriate word for it. Okay. You can do that.
So if you have a picture of cat,
Mm-hmm.
embedding of that image
Mm-hmm.
and a vector for cat will
Mm-hmm.
be in same area. That's
Yeah, we want to, yeah. In the 300-dimensional space, we want those two vectors to be, ideally, we want them to overlap, for example. Okay.
okay. Oh, okay, cool.
Yeah. It's exactly the idea. And in this slide, actually, the cat example is a test example. So we have like figures of images of dogs and the dog word, images of auto and images of automobiles and the word automobile, images of horses and the word horse. We have, let's say, we have the shared space, and we are ensuring that the embeddings of the images corresponding to their labels of the words. Now, if you get an image for a cat, let's say we did not train it, hopefully the image of the cat is close to, first of all, the image of the cat is close to images of dogs in terms of the embedding space. Okay. Um,
Yep.
because there's some commonality in their features, and so hopefully till you get all the way to the final layers of your convolutional neural net architecture, they will probably share similar feature detection aspects. Okay. Not just that, and then also that cat is close to the images of dogs, and the cat word is close to the images of the embedding of dog word, and so you may potentially even align these two. Okay. But these are all, I guess, these are research ideas, just to give you a sense of, you don't have to restrict yourself to a classification task to learn an embedding. You can do these bilingual embeddings or general shared embeddings and so on. Okay. For example, in this figure, you're looking at the embeddings of the word dog images as well as dog word, and you can get the cat images embeddings as well as the cat word to fall close to the dogs rather than the other classes. Okay. Yeah, that's a question.
Yeah, so these are the techniques that we use to learn the embeddings rather than the application of it.
So here it's actually combined. It's not, so here the W is not, it's not pre-learned. It's learned in a way that there is a shared embedding space between the images and the words. Okay.
Okay.
So the first example, so the first, I guess, example, and we're going to revisit it, the classification task and learning at the word embedding. There, the classification task was irrelevant. We just wanted the embeddings. Once we have the embeddings, we would do various things, try to understand, uh, you know, understand them by projecting them into two dimensions, as well as use them in other tasks like uh, other classification tasks which are actually meaningful that you want to do with words, right? So whatever NLP task that you're doing, you can actually use embeddings there, to map the words which are actually not numerical objects to things which are numerical, like vectors. Okay.
Okay. Yep.
But here I'm just showing you a task where you are learning the embedding as well as learning the embedding using training data, such that a test instance you have a cat image. You can actually align a cat image to the cat word because those two embeddings would be close to each other, even though in training you didn't see them. Okay.
Okay. Okay. Cool.
Um, it's good to see these papers. I'm just presenting some research ideas before going into a more simpler idea, which is word-to-vec. Okay. Um, any questions after this part? This was what I covered towards the end of last lecture, a little bit quickly. Okay, if there are no questions, let's come back to word2vec. Okay, word2vec is an example of how to get embeddings, how to get good embeddings. Okay, so this is proposed in 2013, and uses a predictive method. If you recall, there were a couple of ways to get the semantic meaning captured in your embeddings of words. One was count based, where you would just create first a matrix, which is vocabulary size vocabulary, which would just count the number of co-occurrences of words and on it to get embeddings of the words. Okay, and there are pros and cons for that type of a method. But the end goal was to get an embedding, and you could get an embedding using count-based methods as well. And we have not discussed that in detail. A predictive method is what we discussed, where we would have a classification task preceded by a word embedding function or a matrix. Okay, and we discussed an example classification task earlier. We're going to specialize it to word2vec today now. Okay. So in particular, Word2Vec actually has the work done in 2013 had two different types of classification tasks. One is called continuous bag of words task, and the other one is called skipgram. So we're going to go through the skipgram model, the classification task in detail now. Okay. So what is the task? So what we want to do is so I'm telling you the model here, but actually let me start with the task and come back to the previous slide. So what is the task? Okay, so I'm going to describe the task, and then we'll tell how it may lead to good embeddings. So what is the task? We have a bunch of English sentences. So we're going to do is the following. First, we'll pick one sentence out of our collection of sentences, paragraphs, articles, whatever it is. So let's say we picked one sentence. Then what we're going to do is pick a word. It doesn't have to be in the middle. I mean, pick a word from the sentence. And then what we'll do is pick another word, nearby word from this sentence at random. Or it could be even exhaustively, I can pick a nearby word. Okay. So by doing this we are actually creating what is an essentially an input to my task. Okay, so my input to my task is going to be a word pair. It's going to be a word and a nearby word to this word. Okay, and there's an example in the next slide. So that's my input. Now, what is the output? The output is going to be probability that this word is probability of this word in our vocabulary. Sorry, probability of any word in our vocabulary the probability of that every word in our vocabulary being this nearby word. Okay, so we have a word W1, and there's another word W2, which is a nearby word. I want to take W1 as an input. So sorry, I said the input is a word pair. Sorry, this is not correct. Okay, so input is a word, and we want to predict another word. Okay, so we want to predict. So we have a vocabulary of size capital V. So any of these words can be a nearby word. But we want to say that one of these words is going to be a nearby word, and which word it is. For a training example, let's say W1, W2. W2 is the nearby word for W1. Okay. So let me actually explain that with an example in the next slide. So actually, let's do this. So again, I'm describing just the task itself, and then we'll talk about the corresponding neural network or corresponding, the W matrix and so on. So let's say the quick brown fox jumps over the lazy dog is the sentence. Then I'm going to construct now training samples. Okay, the training samples are examples. Right? There'll be an input and there'll be an output. So the input is you pick some word. You can pick every word actually. So pick word, let's say the first word, and then so that's going to be the input, and the output is going to be quick and brown. Okay, so those are the quick and brown are the two nearby words for this word. Similarly, let's say we pick the word fox. Quick and brown are nearby words, as well as a jump and over are nearby words. So I'm going to create 4 training examples. Okay. So each example will have an input and an output. Okay, and so once I tell you what's the input, what's the output, what you're trying to do here, the task is now a little bit more clearer. It is that given that input word, I want to predict the output word. So given word fox, I need to predict quick. But you can see that given the word fox, I also want to predict brown. So 2 examples seem to be predicting 2 different things. So that's okay. And again, Fox needs to predict jumps, and Fox needs to predict over. Okay, so those are the training examples related to the word Fox for this sentence. And Fox could appear in another sentence somewhere else, and that will have its own nearby words, and Fox should predict all these nearby words in that other sentence. Okay, so that's the task. Okay, and we just chose. I mean, to choose what is nearby, we just chose a window of size 2. So you can see plus 2 words to the left, plus 2 words to the right are defined to be nearby words in this example. Okay, in this example as in the word-to-vec construction as well. So now let me come back here. So W will actually again be a matrix. So W will have to have vocabulary size something. So 300 is, so we'll try to get to a full description of our W matrix and the classification tasks parameters. And you'll see that W is going to be a matrix of this size, okay? B cross 300, where B is vocabulary size. And here actually I'm giving you information about the classification task itself. The classifier itself will be a single hidden layer neural network. Okay, so I'm going to describe that in the next slide. Okay, so is that clear what the task is? At least the task is to just predict. So my training example is a bunch of word pairs. I want to predict, given a single word, what's the probability. So given a single word, try to predict the second word. And so since I need to predict, so if you think of a classification task, what is the number of output classes? The number of output classes is the size of the vocabulary itself. So given the input word, let's say test time, I would get a bunch of scores, and the scores, there's going to be one score per word. And so it's going to be huge. And hopefully the score for the word, which is actually the nearby word, is higher than the remaining words. Okay, so that's what we want to get to. Okay, so here's the description of the network. Let's say we have 10,000 words. Then the input word is going to be, so let's say there are 10,000 words in vocabulary. So how are you going to input this training example? So for each word, you can hypothetically think of creating a one-hot encoding vector. Although we don't need that interpretation, you can just think of, okay, how am I going to pass the word fox? I'm essentially going to think of, oh, okay, I have 10,000 words. Let there be a 1 somewhere and zeros everywhere else. Okay, that's a one-hot representation for this fox. But we don't really care about this. This is not our embedding itself. We're gonna we care about W, and I'm going to tell how W is related to this initial representation, the one-hot representation. Okay. The true label is also a 10,000 dimensional vector, right? So remember, we are doing classification. As I said, I told you the output scores will be 10,000 dimensional. So one of those coordinates should be 1 in the true training data if you want to represent the training data. Okay. So your neural network has to output 10,000 scores, and you can pass it through a softmax operation. And what does each coordinate of this output of this neural network represent? It's just the probability that this particular word is the randomly chosen nearby word. Okay, is actually that nearby word that we had in this, for let's say in a specific training example. Okay, so in terms of a diagram, so let's say this is the one-hot representation for the word. Then we have to produce a bunch of scores, right? And all these scores are basically a score for which word is going to be a nearby word for this input word, right? Now, our neural network is going to be represented by directly by a one hidden layer neural network. So we'll have a transformation from this 10,000 dimensional vector, this 10,000 dimensional vector, to 300 dimensional hidden output. Okay, hidden layer output. Now this 300 dimensional hidden outputs, 300 is a specific choice that they made in this particular implementation, word-to-vec, but you can go with any number. So so the hidden layer output is 300, and from 300 again you can go to 10,000. So that's the network. So there's only one hidden layer, and its size is 300 hidden units. Okay. So there is some transformation, right? So there's an input vector here. there's some transformation, and there's some other transformation. Okay, so let me just call it W1, W2 now. There's a specific notation I'm going to use in the next slide. Okay, so that's it. So these are the two parameters in this model. You can also have biases. I don't think I have described biases here, but this is the whole network. Okay, and so you're producing a 10,000 dimensional output. You're inputting a 10,000 dimensional input, and by minimizing the training error, which is to ensure that the output is very similar to the true nearby word, you will get the word embedding. And in fact, just to give a teaser, the word embedding is going to be this W matrix. Okay.
So what is the true label? So if we have a word pair,
Yeah.
the second word in the word pair will be one in the output, right?
Yeah. Let's say ands and able. Let's say this is a word pair for some
Okay.
reason. Okay. So the ands will have a input representation, some one hot representation. Able will also have one hot representation. That's a true label,
Okay.
right? 0, 0, 0, 0 somewhere, 1, 0. So that's the true label. Ands will have some vector, right? 1, 0, 0. You want to go from here to here.
Okay.
Yeah.
So we have to do this like if we are doing it for ants as a word, we have to do it like let's say there are 300 words. We have to do the same thing for 299 times, right? For just one word.
No, no. So you're talking about so let's say fox, right? So there are 4 examples corresponding to fox, right?
Yes.
So just think of each example. You want to match the input and output
Okay.
vectors.
Okay.
That's it, right?
Okay.
So you have pre-generated these examples from beforehand, and then you're
Okay.
just trying to fit the network.
Okay. Yep. Thank you.
You're not going to do it for every pair of words. That's not the right thing to do. Okay. Um, yeah, so I'm just in this slide, I'm just trying to describe what is the size of your trained data. So if your trained data has t words, and if a context window is a size 2, like it's basically the description of what is considered a nearby word, then each word can be associated with four other words, right? So 2 on the left side, 2 on the right side maximum. So the total training data is going to be around 40 or less than that. Okay. So when I said training data is made of keywords, I'm not talking about the vocabulary size. I'm just saying, you just concatenate everything, or, or, or all the sequences of words that you have. Okay. Um, yeah, all the t locations, and then you can just look at 2 left, 2 right, and so on. So basically, your loss function looks like for every word, find all the nearby words, and what's the probability that what's the probability that your network is predicting the nearby word given this word. Okay. So uh, so this is essentially the likelihood function. That's why there's a summation here. All these summations imply this is a log likelihood summation going on. Okay. So we are just trying to fit a model which tries to predict, given an input word, its nearby word. Okay. So if you get it wrong, so you want to pick so you want to say, okay, for the word and, right? Able, let's say, is a nearby word for an example, specific example. Instead of so you just want to find, let's say you predicted a low score for able, then your probability of able given ant will be small, and log of that will be a highly um, negative number. So actually, there's a highly negative number. Um, Whereas if able was correct, then log of the probability of able given ant will be small. This p probability will be high, and log of p will be um, negative, but not too negative. Okay. So sorry, I'm just trying to relate this to your cross entropy or the usual loss function you've seen. This is literally the cross entropy loss function. Okay. We're just picking because why the output was just 1 at the right location, we're just picking up that probability at the right location. Everything else is multiplied with 0, so those terms don't appear if you're thinking of a cross entropy loss function. Okay, so now let's talk about the parameters, because one of the parameters is going to be our embedding after we do the training. So the W matrix. So let's start with the weight matrix W naught. Okay, let's start with one weight matrix, and we're gonna transpose it, and let's let W naught transpose be equal to W. Okay, why did I do that? Because I want to really think of this W to be our embedding anyway. So just to give that notation, let's say the parameters of my neural network, one parameter of my neural network is W naught, and I'm going to transpose it, and it's going to become clear why I do that. So which is the following. Let's say my one hot encoded vector for ants is something like this. Okay, some vector like this. Now, if you think of the W matrix, okay, the W matrix. So W naught. Remember W naught. If it's the parameter or the weight matrix corresponding to the input to the hidden layer, then it has to be of dimension 300, which is its output, the number of hidden outputs, cross 10,000, right? W naught has to be that. The output size is 300, right, for that matrix, and the input is it's getting multiplied by 10,000 dimension vector. But I just transposed it, so you can think of the input as this row vector, and W itself. So W naught is that. So W, which is its transpose, is going to be 10,000 cross 300. Okay, it's a vocabulary size cross 300 matrix. Okay, and what does this operation do? This times the W matrix is just going to pick the row corresponding, which we'll think of as corresponding to the ant ant word. Okay, so so just to kind of understand, if you have a vector 0, 1, 0, and if I have a matrix A, B, C, okay, something like this, then the vector that you're going to pick out, the output is going to be D, E, F. Okay, and if the input was 1, 0, 0 times the same matrix, the output is going to be A, B, C. Okay, is that fine? So you just multiply with this this matrix. You can see that the output is going to be this. Okay. So what I'm trying to say is that if you multiply the one hot encoding vector of, let's say, and, then you're just going to pick up some row in this input weight matrix. So in this, I guess the weight matrix corresponding to the initial, the mapping from input layer to the hidden layer. Okay. And that vector is going to be of size 300. So we're going to interpret that in the mapping from the input layer to the hidden layer as our word embedding matrix. Okay, as our word embedding matrix, and that's why I use the notation capital W. So yeah, so this is a W, and yeah, this is the same W, but yeah. So word lookup table is this W matrix here, and this is just a W naught transpose. Okay, so W naught is that hidden layer weight matrix. Remember that output is 300 neurons, input was 10,000 dimensional vector. But instead of that, we'll think of this matrix. And so for this matrix, you really don't have to do any matrix multiplication. So if I have ants, I'll just look at the ants row and pick up that that vector and move forward. Okay, move forward is in the sense that pick up that row, and that's going to be my hidden vector. And then move forward just means that hidden vector is going to be again multiplied with another matrix to get to my scores, right? Remember, we had to do a 10,000 dimensional scores vector for this classification task. Okay, so I mean, so this is okay. Let me just look at this slide. What I explained earlier is just recapped here. If you multiply this row vector for, let's say, for cat instead of ants, then you're just picking up some row in that W matrix, and that row will be passed on for future processing. As in, that row will be multiplied with the next matrix corresponding to the output layer, and then you'll get the scores, and then you'll see whether the score for the nearby word is high or low. Okay. Yeah, and I said you get the vector, let's say for ants or cat. Then you also need so this vector, when it multiplies with the output layers matrix, then you're gonna get a bunch of scores. So scores is equal to how we use a different notation. Okay, scores is equal to some, let's call it, for now I'm just going to call it a matrix G times the hidden vector. Okay, H was at 300 cross 1, right? That's the output of the hidden layer. Scores has to be 10,000 cross 1, which is one score per word, and G is the matrix which gets you to scores, and then once you get the scores, you can do the softmax operation, right? So e to the power s, that's a score, I divided by some original scores gene, right? So this is the softmax operation, and you'll get the probabilities of for each coordinate of your output, right? So I just call this G. What I want to say is that in word to vec, this G is also chosen to be, so this G is of size 10,000 cross 300. So this G is chosen to be the same as W. Okay, G is chosen to be the same as W. So remember, in a neural network, there's a transformation from input to hidden to output, right? Input to hidden was using the word embedding lookup table, and hidden to output is also going to be with the same matrix. Okay, that's a choice that they made. This is like in general they call it weight tying, and not just in the embeddings, but if you use the same parameter elsewhere. For example, remember in CNNs we were using the same parameter for a filter with with the same parameters we were creating the outputs of several neurons, right? So here we're just doing the same thing. But we'll talk about why this restriction is not going to be really a restriction. So so that's completely describes the network. And now let's talk about why does this learning, why does this minimizing the cross entropy loss or binary cross entropy? Actually, not binary cross entropy, but um, softmax loss over W, over this training data, right? Word one, word I, WJ pairs gives us a good word embedding. Okay, so the intuition is what we've been discussing earlier, which is that if we have similar context, if different words have similar context, which it means that, so when I say context, word and words have similar context, just means that if you're talking about a cat in an article, you're going to use some surrounding words, right, to describe what your article. And if you use the word dog in the article, the words surrounding it, they are going to be likely to be similar to each other. Maybe not exact overlap. Maybe some words are specific to the dog word in terms of them appearing nearby. Some words are going to be specific to cat when they're appearing nearby. But there are going to be some words which will be common. Okay, so which will describe the cat as well as the dog in terms of them being nearby. And then what we want is to ensure that the output probability. So there'll be, for example, there'll be a cat and a nearby word X, whatever it is, and there'll be a dog and a neighbor word X, right? For both of these, we want the probability of X given cat to be high, and same thing, probability of X given dog to be high, right? So that's what we are trying to ensure that, we're trying to train the W matrix, the embedding such that this is high, okay? And I think I have a description. Oh, no. Okay. Um, and you can see that this can happen if the uh, the word embeddings themselves are close to each other. And why is that? Because the if you think of the cat input representation in my training data and the dog input representation, they're one hot encoded. So their distance is always 1 unit away. Okay, they're not similar to each other. If you think of in terms of, let's say, Euclidean distance between them, or any sort of distance, Hamming distance, it doesn't matter. All I'm saying is in one hot encoding, there is no relation between cat and dog. It's the same relation between cat and dog as it is between a cat and a house, for example. Now, but we want the output, right? Output probability of X given cat and probability of X given dog, these outputs to be high or similar, right? Maybe close to 1. So if the outputs have to be the same as in close to 1, then the only thing you can change is the entries of W matrix. Okay. Um, if outputs have to be 1, let's say this is the output, it's coming from hidden, outputs have to be the same, hidden vectors have to be the same. If hidden vectors have to be the same, the input has to be the same, but input is different, right? There's a 1 for cat somewhere else, and there's a for the dog, 1 is somewhere else, okay? Because input are different, only the W can change, it's a linear transformation, so that these two map to the same thing, okay? The same output. So that's the intuition. Any questions about this? Right. I guess this was a key point about word to vec, or any, why we are getting similar word vectors for similar words, as long as they appear in similar contexts, is because we have this two-layer neural network. Actually, there's no nonlinearity. So when I was talking about the hidden layer, there is no transformation. So this where is the network? Yeah. So there is no. So if you think of the activation function as unit, as the identity function. So if you want the outputs to be the same, since inputs are different, one hot encoded, essentially the word vectors have to be similar to each other. Okay, the embeddings have to be similar to each other. So that's how you train. And uh, yeah, so I guess so as I was saying that the matrix is going to be large if you have 10,000. In fact, it's not really 10,000. I think they train it on much larger vocabulary. So the number of parameters is going to be really large. So instead of two weight matrices, they just make the second weight matrix equal to the embedding. So the first weight matrix, so going from 10,000 to 300, let's call it W transpose for simplicity. So because it's not, so W is, so W transpose is of size 300 cross 10,000. And then from 300 dimensions, you're going back to 10,000 scores, 10,000 dimension scores. So that I'm just calling it as W. So W is going from 10,000 to, sorry, from going from 300 dimensional vector to 10,000. And so this is a neural network. So this is the input, this is the output, and this is the hidden layer.
And we don't apply any ReLU or anything? You said it's a linear.
Yeah, so here they don't apply any nonlinear.
Okay.
Yeah. So you can apply if you want to create your own auxiliary task and your own embeddings, but in this particular specification, they don't.
Okay. So we have a different input and we want to go to a similar output.
Yeah.
Then like naturally you would think that the W has to be different, right? Because
So okay, so I guess I'll just quickly recap why. So think of it this way, right? So output, it's 10,000 dimensional vector. So let's say there's one long and everything is 0. Okay, so that's a nearby word. Let's say there's a cat and X. Let's say this is the word X. Could be anything. And there's another training example, dog and X. Okay, because you need to see this to say that cat and dog are similar to each other.
yes.
Not immediate, but for simplicity, for this example, let's say this is true. Okay, so this is the output vector. Now, in terms of the hidden layer, if you want this output vector, you want to have similar hidden layers. So if you want to, so let's say W is fixed, it's a linear transformation. You want a certain coordinate to be high and every other coordinate to be low. The linear transformation can only give you so much. So in the sense that the hidden vectors have to be similar to each other. Okay. Because it's a linear transformation. And then because hidden vectors have to be similar to each other, now you go back to the input. Input, we know it's one hot encoded, if you really think of it as a neural network. Cat is one somewhere else.
Yep.
And dog has some one somewhere else. Okay. These two are not, and so both these input transformations have to lead to similar hidden vector. Okay, and to do that, W is going to capture that. So the entries of W, so the W's rows will capture that.
And we want them to be similar to each other, right? Basically.
Yes. The parameters will capture that because the input is constrained to be, it's just one hot encoding. Okay. So there has to be somewhere you have to say, so you can't change this. Right? These are fixed. The only thing you're saying can change is entries of W. Now you can change the entries of W so that both cat and dog lead to the same high probability thing.
Okay. Cool. Yep. Okay. Thanks.
I mean, so I'm just really reverse engineering why you would find similar vectors for cat and dog. Okay. Yeah, because you'll have some contextual overlap in your training data. And you want to produce the same high label for X for both these examples. Okay, so there's some engineering tricks in Word2Vec to actually deal with this large dimensionality because English vocabulary is not 10,000; it's actually much higher. So you can do a few things. For example, you can subsample frequently occurring words. So you can, you can, sorry, if there'll be an outsized number of pairs such as D and something else, right? D and X. There'll be so many such, articles plus something else as word pairs. There'll be so many. So you can drop them. You can, try to normalize the frequency of less frequently occurring word pairs. You can boost them up, and you can reduce the number of samples where it's very high frequency occurring word pairs. Okay, so that's one example, one trick. The other example is to treat an entire phrase as a word. For example, you can have um, um, like gas powered is a word by itself. Okay, and it's not actually a word. Gas is a word and powered is a word, but you can think of the whole phrase gas powered as a single word. Okay, you can do that. And also there is something called negative sampling. So you can update only the weights of the neurons corresponding to only like a few non-nearby words. So um, I think we'll skip negative sampling here, but it's just an engineering trick to say which weights get updated when you do this. Let's say you have a word pair cat and X, right? So when you update when you do backprop, you have to update the whole parameter, so which is W, the whole entries of the W matrix. So you can actually only update, what you do is you only backprop from, so let me just go back to the picture. So you have this, so you only backprop from a few entries here. Okay, so recall to do a backprop, you have a loss function. The loss function will go back to scores, right, in terms of computational nodes, and then scores will go back to the parameters, which is essentially these W's, right? So instead of backpropping through every score, right, to get to W, you only pick a few of them. Okay, I pick a few of the non-nearby words. So instead of 10,000, so one of the words is a nearby word, right? You pick from 10 others and just use those scores as it's basically a reduced computational graph. Okay, so to update the entries, and so you'll only touch a few entries of your W matrix in that sense, in that way. Anyway, so these are the tricks that they employ to deal with the dense W matrix, because if you think of the number of vocabulary size times let's say 300 or whatever is the number of dimensions that they chose, it's going to be a really huge matrix to work with in terms of updating and so on. Okay. Uh, yeah, I mean, so vocab size is actually 3 million. And you can actually look at what is the vocabulary, like what are the words in the vocabulary or word phrases in the vocabulary in the snapshot. And you can actually look at you can actually download, and you can download the version which has 300 dimensions as the embedding size, and you can actually quickly check what are, for example, nearby words for the word good. Okay, I mean, not just good, this is just an example. You can download and try out these word embeddings. They're available through various packages. GenSim is just one of them. You can also download it from other packages. I will skip the continuous bag of words representation, but it's okay. It's just one slide. So let me just explain what the slightly different task is. Here, the classification input output is the only thing it changes. So input is going to be the nearby words. Okay, the 4 nearby words, and the output is going to be predicting the one word for which these guys are the nearby words. So so think of if you think of the this where is this? Yeah, here output is going to be, you want to get the coordinate for Vox, so coordinate for Fox, the score to be high when you give a quick brown jump and jumps over as the inputs. Okay, so now you have four words as inputs. So these 4 words, first you create the one-hot encoding, and then essentially taking them as input is essentially picking the rows corresponding to the W matrix, 4 rows. But they all have to ensure that on the output side, you have a high score for the Fox coordinate, and everything else should be 0. So that's the continuous bag of words subtask. So you can use either task to get to very similar embedding. Okay. And there are other pre-trained embeddings that you might have heard of called Glow. It's also available. It's pre-trained embeddings of words, English words. And there are actually many more in recent times, not just for English, but also for other languages. So you can uh, download them, and at least since they are pre-trained, you can just do nearest neighbor search to figure out whether the word embeddings make sense. And you can directly use them instead of doing one-hot encoding if you have a textual machine learning task. So any questions about this? Just go here. So one of your assignment questions will be about using a pre-trained embedding. So you can play with either Glow or one of these embeddings in your assignment question. I mean, the question will be about actually doing translation. So in that task, you can use pre-trained embeddings to improve your solution. Okay, if there are no questions, let's move on to lecture 5. Um, okay, so what's the learning goals for today? The learning goals is for us to introduce and understand what is a recurrent neural network, and we'll look at a couple of specific examples of recurrent neural networks. One of them is called an LSTM, long short-term memory network, or LSTM layer block. And then we'll look at a few examples where these types of models make sense. And this class of models are actually very useful for sequential data. So think of time series data, but but the data is not actually numbers, as you saw time series methods maybe in a classic, in a more earlier course. But here the time series could be a sequence of words, a sequence of objects, any arbitrary objects, a sequence of images, for example. And so that's the class of problems we'll be looking at, sequence to sequence learning. So we look at LSTM, and towards the end, we're going to also try to look at some examples and how LSTMs are fit in there. Okay, so we're going to look at RNNs. Many of you might have heard of it. So before that, let me just classify the different classes of problems you can have. Okay? So these are all again supervised learning task, different types of supervised learning tasks. So the type of task that we are most familiar with is a fixed input, fixed output type of task, where the input is, like for example, word to vec, the input was 10,000 dimensional, output was 10,000 dimensional, right? But many of the problems that you also worked with in your assignment, for example, they're fixed input and fixed output. The input is of a fixed size and output is of a fixed size. But you could also have many other types of tasks. For example, one of them is a fixed input multi-output. Okay, so whereas you provide a single input, but you're generating 10 outputs or 20 outputs. Okay. So this, for example, in the context of today's discussion, this could be, for example, input can be an image, and the output could be a sequence of words that kind of describe the image. Okay, if you had training data where you had images and text describing those images, and text describing those images was your output, then you can actually go from an image to a sequence of words, and that would be essentially an image captioning task, and that's this task. Okay. Similarly, a task that we've already seen last time was this sentence classification, right? A sentence classification using RNNs. Then the input is a variable length sequence. It's a sequence of words, and the output is the class of that for that sequence. Okay, whether it's a positive sentiment or a negative sentiment, for example. And now you can see that once you have one-to-many and many-to-one, you can also have many-to-many, where there's a variable length input and a variable length output. And a very popular example there is machine translation. Okay, going from, let's say, one language to another language. And of course, a special case of that is kind of fixed here. Both are examples of many-to-many. But you can see that you start generating the output the moment you get the first input, Whereas you here in machine translation, you start generating the output the moment you're finished with the input. In some sense. Okay, so that distinction is not very important. All I'm saying is there's sequence to sequence. These are all, so this class of problems are basically sequence to sequence class of problems. Of course, the first, second, and third examples are just special cases of this, right? Where it's not a sequence, it's a sequence of, it's a trivial sequence where it's a fixed size. Okay, so sequence to sequence problems have a special have a special thing that we want to capture in these types of problems, which is the idea of persistence. So basically, we want to have in sequence to sequence problems, the output should depend on what has happened, not just at the immediate input, but maybe two inputs before, right? So there has to be some persistence of information. Okay, for example. Like for example, if you're using a feed-forward neural network or a CNN, okay, to classify every scene in a movie. Okay, so you have a scene, um, and you are trying to classify it as of type A or type B or type C. Um, but so it's unclear a priori, at least. I mean, you can certainly change things, but a priori it's unclear how you can use a regular convolutional neural network to use information from previous scenes. Okay. So that's what I meant by there's no persistence. So if let's say you're classifying first scene, you're classifying second scene, classifying third scene. There's no information that you're exploiting from what you did before. Maybe the last scene was a scene of type A, then maybe the next scene is going to be of type A itself, or maybe something very similar to the previous scene, rather than a completely arbitrary scene, right? So there's some spatial information that you can try to use, which if you directly apply a classifier again and again, which ignores the sequence, will not exploit. Okay. So RNNs are able to exploit this information, and here's, so generally when people talk about an RNN is actually a larger network. But when people draw it, they show a drawing which looks like this. Okay, where there's an input and there's an output and there's some processing. So there's a processing done by this, let's say, the block, which is a network, neural network essentially. And there's going to be a uh, feedback loop going from A to itself. Okay, so basically there are two inputs to A and two outputs to A from A, right? So this is just a compact notation. You can expand it out and think of your actual neural network as this. Okay, so x naught is input. So let's say we have a sequence of length little t. Okay, 0 to t. Then all these are inputs, and I'm going to produce outputs. Okay, at every time point. But maybe there's only, the output that I care about is the last one, then I'll focus on that to define my loss, for example, for this input sequence. And it's the same block being used again and again. Okay, so that's the, I guess, a recurrent aspect of it. That is, I'm going to use the same block again and again. Okay, so the sequences x0, x1, x2, all the way to xt can be either images or words or even numbers or vectors. Okay, so so if they're numbers, you can think of one-dimensional time series modeling. You can do that using RNNs. Um, so let's now. So what are we going to do in the next few slides is get to dig deeper and deeper into what this block A is and how does it capture the notion of persistence. And we're going to specialize to LSTM soon. But before that, let's keep it to a simpler network. So this is called an unrolled diagram, by the way. So unrolled diagram is just, we just went from a rolled up diagram where we just put a feedback loop through this arrow to an explicit description of how is information, how is computation happening. For example, this essentially kind of resembles a computation graph, right? So x naught is being taken as input, some computation is happening, some output came, intermediate output came, this output plus the next input, some computation is happening, some output was realized, and so on. So it essentially resembles a computation graph. So if you look at a stage, they accept an input and give an output, which are parts of the sequences. So if you look at a stage, so this is input, and I'm using H because you will see that H essentially is the hidden or latent vector, unless it's actually used for computing losses, or actually used to, say which class, or whatever is the output decision for your modeling task. Okay. Uh, so let's so let me expand out what A is, so that it becomes clear what the full computation graph is for recurrent networks. For that, we'll use this following notation. So we'll use the yellow block for for a single neural network layer, uh, like a feed-forward network layer. We'll use boldface, directed arrows to represent vector transfer. So the vector is a vector is going from here to this block. If two arrows merge, it's concatenate, and two arrows diverge, it's just a copy. It's the same vector being passed on to two outputs. Okay. So with that, now we're gonna zoom in on what the A block is. So you can actually write this RNN directly, for example, using PyTorch. It's basically this. So you're getting a input from the previous. So you're getting two inputs. Remember, it's always not always, but in this example, it's two inputs and two outputs, right? So you just have to define this block. Okay, it's RNN, right? So some function called RNN, which takes two inputs, like ht minus one and xt, and produces ht and maybe ht itself, if it doesn't have two different outputs. So these two inputs, first xt and ht minus 1, are concatenated. So that's the concatenation operation happening here. This is a single layer of a neural network, and the word inside it represents the nonlinearity that I'm going to use. So we're going to use tanh in this example. So tanh is a nonlinearity, and it's a single layer. So it just means that um, there's a tanh of a single layer. So there are some weights times its input plus some bias, right? So the input is going to be ht minus 1 and xt. So concatenate them. That was the concatenation operation. Okay. Because it's a layer, it will have a weight matrix and let's say bias vector. So you compute that. You apply the tanh transformation. So this is your essentially ht. Okay. So, and ht was passed on to the next RNN block, as well as is output. I mean, it's available. You can read it as an output if you want. Here is the example in code. So we are not really using torch here, but so in code, if you define the class RNN, you just have to define three things: the two parameters and one place to store the hidden, store the previously computed vector, right? ht minus 1. So I need to remember what the t minus 1 h is. So these are the three things that you can initialize. So it's essentially like a memory, right? So you have to remember what ht minus 1 is. And then if you step through an RNN, you give an xt, then you just have to use w and concatenate horizontal stack. Just means you concatenate exactly what I wrote here, or you stack these two. Um, and then add bias, and then you apply tanh operation, and then just return the h. Okay, so that's the RNN. And so if you instantiate the RNN with some input dimension and hidden dimension, hidden dimension is 3, input dimension is 4 here, and then you can given you can run a for loop where you can keep feeding xt's, right? So here I'm just creating a 4-dimensional random vector, and then I keep feeding it, and you can just see the output. Okay, see the output at every step, and so we are just replicating what is happening here. So we provide an input, and that input plus the previous time this RNN block acted, there's an output. So that output plus this input is concatenated and processed. Okay. Okay. So what we'll do is Okay. Okay, so what we'll do is take a quick break and resume at 4:57, and then I'm going to talk about the this example in a little bit more detail with numbers. Okay, so before we get to the numbers, let's take a break. And if you have any questions, uh, type in the chat or ask me directly now. Okay, I think I missed a couple of questions from earlier, so let me just cover that and then let's take a break. So, does brown or quick have more or less weight associated with fox? So they don't have more or less weights because remember in each training example it's just fox and brown, fox and quick. If it happens that fox and quick has appeared in other sentences many times, those you can think of as additional examples, and so that means that fox and quick may have a higher weight essentially in terms of because there'll be more loss terms for one for each example. So if there are many examples which have the same pair, then that example pair will have a higher weight. Second question was what will happen if we have a new unseen word. So if we don't have if we have an unseen word for which we don't have an embedding, is that the question? Then, yeah, I mean, so if we have an unseen word, we cannot. I mean, we don't have an embedding for that. So, but if you're saying for that classification task in the test set, if we have an unseen word. So no, we have our output is always going to be on the whole vocabulary. Now on the input side, if we don't have a word which happens to we never had the input side a word which 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 is in the vocabulary but which never happened to be on the input side, then we'll not learn its embedding. It will be just random numbers. If we start if we start our training with some random initial w, that 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 row for w will not change. Okay. But it could change if the two, because we are sharing, so we are using the same uh, w for the hidden layer as well as the output layer. So the parameters corresponding to the unseen word on the input side could still change when you do backprop because of the mapping from hidden to output. When you backprop from score to the hidden layer, the w entries can change.
But do we make the vocabulary from the input data, or vocabulary
Yeah,
is
yeah, it's a great
fixed for?
question. Yeah.
Yeah.
So ideally, you want to make a vocabulary which does include all words that you'll see in the future once you, let's say, learn your embedding. But typically, you should make a vocabulary using the union of all the words that you'll see in your data set. So including training and test, because that's really not data snooping. It's basically to say that, yeah, these are the whole universe of words that you'll have.
Okay. Cool.
How is the issue for unseen word tackled? So if the word is not seen, you don't have an embedding, you can start, you can, okay, if you don't have an embedding, it's a good question.
Isn't there like one unknown, like you put just unknown, and every time you see unseen, you just update that weights?
So you can certainly use, um, there's a few ways to do it, but I don't know what's a good way. You can, you said, as Nisarg said, you can use you can map that word to an unknown, and unknown can always have a embedding from your previous uh, in your previous training data. For example, you could have an unknown and you could do something by having an unknown token, or you could uh, yeah, you could do full retraining with that word if you have examples related to that word and its context, for example. Um, yeah, I mean, so I don't know a good answer for that. Yeah. Okay, let's take a break till 5:02 and then come back. Okay, so yeah, welcome back. Um, so this question about if you see encounter new words when you don't have, which you've not seen in your vocabulary, for example, or you don't have a word embedding for, what do you do with it? There are several engineering solutions that you can try to use. One example is which is to, for example, drop the word. You know, if you drop a word, if if it's not important, it's fine. If it's important, then it's not good. Otherwise, you can, if you have prior information about the word, then you can actually just use the embedding of a neighborhood word related to it. For example, if the word is a synonym to another word for which you already know that, although this word was not in your vocabulary when you're trained, but this is a synonym for a word that that's already been trained, then you can just use the other word representation if you want. So there are many ways. Maybe there are others. You guys can try to find it out. Okay, so now let's come to an example to understand a little bit more about how RNN is going to work. So for that, we'll look at language modeling. So language modeling is the task we discussed last time. Using Markov models, right? So what is the language model? And we're going to look at a specific type of language model for this example, which is going to be a character level language model. So we want to take in as input a large text database, or basically a bunch of sentences or a bunch of paragraphs, articles. We want to input it into our recurrent neural network, and the network has to model the probability of the next character given whatever it has seen so far, maybe a sequence of previous few characters. Okay. And so what's the use of language model, not specifically for this character level model that we're going to talk about, is that you can generate new sequences of words, and hopefully those words will also capture some grammatical aspects, and so it will essentially be a new sentence generation, right? So a very, I guess, famous example, in this uh, in the past few, I guess, months is GPT-3. Okay, so so let's look at the star example now. So let's say our vocabulary only has only 4 words. Okay, so four symbols or 4 characters: H, E, L, and O, and we only have one training sequence for the discussion, which is H, E, L, L, O. Okay, so this is the training sequence. This is our vocabulary size. So vocab size is 4, and instead of using word to vec, let's use one-hot encoded representations of these words. Okay, um, so 1 0 0 0 0 1 0 0 0 0 0 0 0 1 0, and okay, these are the 4. Let's say these are the 4 representations for these words, numerical representations. Once you get to numerical representations, you can just use them as vectors, as inputs to your RNN. So what are the, so if your training sequence is HELLO, then you can have several training sequences, right? So you wanna, so for example, when you're only looking at H, for example, given H, you can say the probability that, the probability of the symbol E or the character E should be high. Given H and E, the probability of the symbol L should be high. HEL, probability of symbol L should be high, and finally the last one. Okay, so let's look at the RNN architecture. Okay, so first, as I said, we're going to embed these characters into vectors. For simplicity, I'm just showing you a one-hot encoded vector. You can use, if you had pre-trained embeddings, you could use that at the input layer. Okay, once you have these embeddings, how does the RNN work? So it's going to pick H. Okay, it's going to uh, go into the, so the RNN block is going to compute one output, right? So right now there's no input other than this H, okay, H character, in the sense that there is no H, the previous hidden layers output. So let's think of that as all zeros. So the RNN produced a vector which, let's say, is 3 dimensions, okay, as we specified in the pseudocode here 2 slides ago. And given this 3-dimensional hidden vector, you can transform it to get to the output layer. So I don't think I explicitly showed the transformation. So given HT, you can go to um, Yeah, given HT, you can um, uh, go to a O subscript T, let's say, OT as a vector, which is again going to be in 4 dimensions. Okay, it's you just need to kind of produce the next characters representation, right? So given this hidden layer, there's another transformation, and you get a output vector. Now, hopefully, in that output vector, because it's a vector of scores, you are trying to predict the score for the E character. So let's say E is the second character in the vocabulary, so it corresponds to, let's say, the second coordinate. Then hopefully the second coordinate is the highest. Okay, which in this case is it is true. 2.2 is the highest among the 4 numbers. Now this hidden layer output at the first step plus the second character, which is in my training example was 0100. These two together will be the input to the RNN. It's going to produce a hidden output. So hidden vector, which is one, this the thing inside the green, is going to be transformed to get to your output vector, the scores. And the scores again need to be such that the score for the appropriate class is the highest. The appropriate class, in this case, we are trying to predict L. So the score for L should be highest. It is not the case here. It's the lowest, in fact. But hopefully, you're going to train the parameters of the RNN such that this is going to be highest, and so on. So this is how the RNN for a character level language model could look like. Okay, the most vanilla version, and yeah. And so how do you compare E with the actual output? So the actual output is going to be 0100, which is what we want. But E here is not that. It's a bunch of scores. So if you renormalize this, so these numbers, you can normalize them back to between 0 and 1 by just doing the softmax operation. And then you can do just a cross entropy comparison, which is essentially nothing but the log probability of character E, which is the second coordinate given H. Okay, so you just pick the second coordinate, actually log probability of, not probability, but so if this 2.2 map to some number like 0.8, then it's the log of 0.8 would be the loss, for example, for that example, the current parameter values. Okay, so all I'm trying to say is that you can define a cross entropy loss at every output vector simultaneously. So you will have a loss to ensure that the first output matches the first, the character that you care about. The second output matches the character that you care about, which is L. The third output matches the character that you care about, and the fourth output also matches the character that you care about. So there will be 4 loss terms, okay, for this the full training example, training sequence. Okay, so yeah, I mean, and the notion of persistence, just to kind of point that out, is that when the first L is input, then the next character should be L, whereas the second time L is input, next character should be O. So you have to remember which which L even though you're at L, what happened before matters. Okay, so for the example here, at this L, you should predict O because previously there was another L that appeared immediately previously. Okay, so that's why you need the notion of persistence. And hopefully RNN captures that because you're passing on information from, so when the second L is passed, you also have information about the fact that there was an L before, and hopefully that ensures that O's coordinate is the one which is triggered the most. Okay. Any questions about this part? This is how an RNN is. And so it's just a neural network where you're reusing the parameters. So I think I briefly mentioned that. It's basically, when in this hidden layer, whatever is the parameter, let's say there's a W, right, which goes from this vector to this vector, and there's a transformation, tan H transformation. The same W is going to be used here, same W and same W. Okay. Now, if you do a backdrop, you can see that if the backdrop and find the gradient with respect to this parameter W, there are several locations from which the gradients will arrive, and so you have to add them up together. Okay, so it becomes complicated, but you can try to do it as an exercise to get a sense of how weights will be reused and how gradients have to be added up. Okay, so that's that's the feature about RNNs. They use the same weights to do the transformation from the input and the previous hidden to next hidden and next output. So any questions up to this point? So if not, we're going to look at a specific neural network, which is a specific instantiation of RNN. So RNN, the vanilla RNN that you saw is actually a full-fledged RNN by itself. So which had a block like this, right? So there was an input, there was a previous layer. So both were getting concatenated, and it was getting passed through a linear transformation and then a tanh, and then it was producing the next output. Okay, tanh, and then the same thing was reported as the output. Okay. So XT, this is HT minus 1. So this is an example of an RN block itself, but we have a more, I guess, empirically more successful block. It's LSTM. There are many other blocks also. I'm gonna briefly mention it towards the end. So let's talk about LSTM.
So, Professor, one doubt.
Yeah.
So, is it like you're passing two inputs for the hidden layer each time in order to process a sentence? Is it something like?
So we're passing two inputs. You can think of this not as a hidden, yeah, you can call it a hidden layer. So this is just a computation block, right? So it takes two inputs, produces two things, two outputs. It's a two input, two output device or computation. So it's just taking two things as the input, producing two things as the output.
So,
Okay.
when you say two inputs, so one of the input becomes the weights coming from the previous word that we trained.
Activations,
Yeah.
HT minus 1, yeah, previous outputs from the previous computation. So think of it this way, right? If you think of a computation graph, so let's say there was some parameter, let me call it WCOMB, used to go from these two guys to something else. Now, for this guy, there was another computation block, right? With the same W comma B, that's all. The same parameters and this HT minus 2 and then XT minus 1.
Okay.
So yeah, so it's in that sense, there's really nothing complicated. So we are just representing this block using, like a square notation with what's, like a
Yeah. Okay.
fancy notation and all that. Yeah.
Yeah, it's clear now. Okay. Thank you, Professor.
So that way, there's really nothing complicated about RNNs. It's just a huge computation graph. Depends on, so if your sentence only had, let's say, 4 words, or let's say your sentence had 4 words and you're trying to do a language model, and then your RNN, unrolled RNN would only have like, let's say 3 nodes or something. But if your sentence had like 10 words, then your RNN could have, in that computation graph for that sentence, it could have, the unrolled version could have 9 nodes or something. Okay. It's just that, but once you unroll it for an example, it's just the same parameters being reused again and again.
Okay. Okay. Yeah.
So let's look at LSTM. Yeah, so why LSTM and why not the vanilla version? I guess that's the question. So why are we looking at yet another? So we already decided, we can do a for loop and we can use one simple, one nonlinearity inside and it should work. But it's just that it turns out that vanilla RNN block that we discussed so far is not really good at looking at both. It's not good at capturing both long and short term information. As it's been empirically observed. Okay, so what is short and long-term information? Let's say you're predicting, let's say you look at the previous 2 words, advanced prediction, and then you say, okay, the next word is probably models. So the immediate predicting words are useful, right? But what if there's a sentence like where it starts with I went to UIC in the beginning of the paragraph, and then I lived in. You want to predict what's the next word. Okay, that's what a language model does. It tells you what's the probability of the next word. So you want to say Chicago. So, but to say that you're in Chicago, you need to kind of persist the information that they went to this UIC, and let's say UIC is a word which has so that you encountered in the past. So there's a long, and in between there could be a lot of words that you come across. Okay, so for this you need more information in the sense that somehow the RNN has to remember, and the way RNN remembers we just discussed here, right? So the only way it can remember that something previously happened is through this previous things that were passed to it. So current thing is getting passed, current input, right? But everything that was previously passed is only captured by the previous input, the second input that it gets. That is ht minus 1. So ht minus 1 somehow has to capture everything about what it has seen, and hopefully it has, and ht minus 1 should be such that, if it has seen UIC, it should influence the output to be such that the Chicago coordinate is, the coordinate corresponding to the Chicago word has a higher score. Okay, so ideally you want that, and that's kind of difficult to achieve. Okay. Um, so yeah, so uh, for example, this output may be dependent on these inputs, and this output may be dependent on several words before there was some input. Okay? So this is I guess a longer term relation, but all information only comes through this edge, through this link, right? So this is the current information, but all the previous information is somehow encaptured in this edge. And so that's kind of hard to do with a vanilla RNN. And so people have tried to experiment with how can we better transfer this information, okay, about what has been previously seen, either words, or if it's an NLP task, or scenes if it's a scenes or images if it's a image related task, or it could be even numbers. Okay, so so I guess the point was that vanilla RNNs are not able to at least remember or learn how to connect or use long range information, as in information that we saw a long time ago. Okay, so and that's why there's a slight variation, so a slight improvement of the RNN block, uh, and it's called a LSTM cell. Okay, it's not really, there's no, it's again it's just a computational graph, but you can attach interpretation to that computational graph inside, like just like this. Where is that block that I drew? Yeah, just like this block here. I can there'll be some different. So just like this node, this block here, there'll be a slightly different block, and we can attach some notions of why it would be able to capture long-term information. But there is no really explicit memory here. Okay, so although it's the M stands for memory, it's not really, there's no storage or anything. It's all computation. Okay, so some input gets transformed to output, intermediate outputs to final output. Okay, so LSTM, which is LSTM recurrent networks, also have a similar structure to vanilla RNNs. Okay, so the repeating module is different. Basically, this block A is different. And instead of a single neural layer, so in the vanilla version, we just had one Danish linear, one bunch of weights and biases, and one nonlinearity, and that was it. Whereas here, there's going to be 4 neural layers. Okay, so the layers are represented using this yellow blocks. So there's 4 layers, and we're going to discuss. So it looks messy if you just look at it in one glance, but we're going to discuss, why this wiring architecture, why this computation graph here, essentially. There is some post-hoc interpretation that you can do, and that's what you're going to do. So just recall, yellow blocks are neural network layers, and we're going to use this circular red or pink circles to represent point-wise operation. Point-wise operation means element-wise. So if I do X and then multiply with 1 and 2, and then 3 and 4, the output is going to be 3 and 8. Okay, so it's just multiply 3 with 1, 2 with 4, for example, coordinate-wise operations. And then this is just vectors, this is concatenation we already discussed, and copy we already discussed. Okay, so now let's talk about, so now we're going to just describe this architecture for the next few slides, next 3 or 4 slides. So LSTM has basically so things which don't change are the input. Of course, the block has to take an input, the block has to produce an output, right? So that is fine. But the block also has to transfer information from its previous block to the next block. Okay. So previously that was done by just one arrow, right? HT minus 1, and there would be the same output was essentially being also transferred to the next block. But instead of that, we have 2 different types of vectors that go from block to block. Okay, and we're gonna, so that's gonna be like a slight difference from previous blocks. So so we're gonna first describe one of these vectors. That vector is called a cell state vector. Okay, and it's gonna it's just designated. It's just called cell state vector, and you can see that it's gonna come from the previous block, a previous computation node, and it will undergo some element-wise operations, right? Products and additions, and then it's just passed on to the next block. So, so there is some vector which is being slightly more, some coordinates are being changed essentially, right? And then it's going to be passed on to the next um, block. And so that's why it's called a cell state. It's somehow like maintaining state with some perturbations inside the state, and it's the same thing is getting passed out, okay, to the next block. So um, yeah, so that this is CT minus one and CT are the cell states at different, cell is just, this block is called a cell. So, but there are a few other, aspects, right? There's these additional inputs and additional outputs that I've not discussed. But let me first describe the cell state fully. So it's run straight down the unrolled network. So if you had, let's say, 4-length sentence, then this block would be repeated, let's say 4 times or 3 times. Then the cell state would run from the first cell all the way to the third cell. Okay. Information, as in, so information is captured by this vector, right? CT minus 1, or so any of these vectors. So it flows along, and it's unchanged if there's no multiplication effect or if there's no addition effect. Right. So if it turns out that there's no additions going on, so all the adds are 0, element-wise additions, or if all the element-wise multiplications happen to be 1, then the information is just going forward, right? This vector, whatever numbers were there, let's say 5, 4, and 3, it'll also be 5, 4, and 3, as long as these two operations don't, change its entries. Okay. But we will talk about how, in fact, the key part is to discuss how we're going to change the cell state. How is this vectors getting manipulated as they go from cell to cell? Okay, as they're being computed at the end of each cell and as they're being inserted to the next cell. So we're gonna add or remove information to the cell state. Okay, so that's what we're gonna do. That's the most important thing. We're gonna try to change the cell state, and that's how we're gonna preserve information from not just the previous cell, let's say 10 cells before. To do that, we're gonna introduce the notion of gates. Okay, gates are like on and off switches, and they let you pass information forward or not pass information forward. So let's say there was this 5, 4, and 3. That was the vector, and eventually I have a vector 5, 4, and 3. Okay, maybe 5, 4, and 0. Okay, that means that there was a on-off switch which somehow changed. That was manipulated so that information, which is essentially this number 4, was passed on to the to the output of the cell for the first 2 coordinates, but not the third coordinate, for example. So gate is like an on-off switch which kind of modulates the entry value. So it's from the input to the output. So again, we are just talking about transformation, some input, a vector input, ultimately leading to vector output, but it gets changed, and that changing behavior is through this notion of gates. Okay. So for example, here's an example. So I think I have the next slide. So let's say V is an input. V is that 543 vector, and the output is 540. Okay, let's say. What do you think this multiplication, element-wise multiplication input should be for this to happen? The element-wise multiplication should be, if you guys can guess, it's 1, 1, and 0. So if I multiply 1 with the first coordinate, I'll get 5. If I multiply 1 with the second coordinate, I'll get 4. If I multiply 0 with the third coordinate, I'll get 0, right? So that's one way to change to FU, V. And to get 1, 1, and 0, let's say I can only produce some, not numbers which are not 1, 1, not between 0 and 1. Okay. Then you'll have to do a linear transformation, and you can also do a sigmoid transformation, right? Non-linearity. So if U's were, let's say, some intermediate numbers, which are like minus 10, 10, and 50, then you have to transform them with some parameters, W and B, and then you can rescale them. It's a softmax operation essentially, so that they become between 0 and 1. And then you do the element-wise multiplication. Then you exactly achieve what you wanted, which is to do, you're only optionally letting some information to flow through. Okay, so this is what is an example of a gate. Okay, and the gate is controlled by local parameters and a controlling input u. Okay, any questions about this? And we'll see several instances of gates in the LSTM block now, the next 2-3 slides. Okay, so in particular, if you think of the sigmoid nonlinearity, so in this previous picture, the sigmoid layer essentially outputs numbers between 0 and 1. So basically, and if you do an element-wise multiplication, it essentially is ensuring how much information in each component of this vector can be passed forward, right, in this output. Okay, so if sigmoid, if the output of this neural network layer, one of the coordinates is 0, it means that don't let that coordinates information pass through, as in make it 0 if I'm doing an element minus multiplication. If it's 1, it just passes through. Okay, so LSTM has a total of 3 such gates to control the cell state. So going from CT minus 1 to CT, we have 3 gates. Okay, and there's some interpretation that we've been given about what these gates control. So the first is the notion of forgetting. So you want to forget old information. So CT minus 1 is the old information, old cell state, and you want to get to CT. You want to forget some parts of the old cell state. Okay, so so the way we're going to do it is yeah. So we're going to use another input from the previous cell. Okay, so we've been focusing on CT, but there's another input from the previous cell called HT minus 1. So in particular, the difference between a vanilla RNN and a regular RNN is the 2 inputs, and the 3 inputs and the 3 outputs. Okay, the previous previous cell is going to produce an output called cell state, which is CT minus 1. But it also is going to produce another input, which is HT minus 1. Okay? And actually, those two are very related, so it's not such big of a difference. Why, we're just calling them CT minus 1 and HT minus 1. The usual XT for this block, and cell state CT is the output, and then HT is the output, which is to be passed on to the next block, and then generally an output, okay, whatever you want to output. Okay, so so to decide what information to forget, we're going to take 2 inputs, HT and XT, and then we're gonna, from HT and XT, which we're gonna form a U that's gonna pass through essentially a sigmoid, and it will do an element-wise multiplication with the CT block, with the CT minus 1. Okay, so how is that happening? It's very simple or straightforward. Is that XT and HT minus 1 you first concatenate, you call that U, you pass it to the sigmoid, then the output of that sigmoid layer will be, every coordinate will be between 0 and 1. Then you do a multiplication with element-wise multiplication with CT minus 1, right? So then you will get some intermediate output where you have forgotten some coordinates, because if you keep if the sigmoid output is all ones, then you're not forgetting anything. If the sigmoid output is all zeros, then you've forgotten everything, because if you do element-wise multiplication with the all 0 vector, then you get zeros at the output, right? So that operation, they show, you can show it explicitly as this. Okay, HT minus 1 and XT are inputs. You have parameters in that gate, WF and BF for getting gate, and then a sigmoid operation. You produce a vector which is between 0 and 1. You multiply element-wise with the CT minus 1. Okay. For example, when is this? There's just a post or some interpretability statements here, which is that, for example, the cell state may include the gender of the current subject, right? So if let's say the current subject is a male, then let's say the gender is remembered in that vector CT minus 1. Now, when a new subject is encountered in the sentence, then you need to forget the gender of maybe you need to forget the gender of the old subject. Okay, so this is one way to, if you can ascribe one of the coordinates to be related to the gender, maybe high means male and low means female, maybe this is a way to, a mechanism to control that. Okay, it's just interpretation though, because all this is just numbers flowing through in and out, and they'll be tuned, these parameters will be tuned to minimize whatever is the loss function, like cross entropy loss or something like that. Okay, so what is the next step? We need to add new information. Okay, so new information was it was, again xt was the new information. So we'll somehow add that to the cell state. So to do that, we'll have two ingredients: another gate, which is called the input gate, and the usual tanh layer, which we have seen in the vanilla RNN block. So what does the input gate do? It just decides which values to update. So let me yeah, so input gate, so there are two parts to the remembering new information. One is an input gate and one is the tanh layer. So decide which values to update and create a vector of new values to update to. So you need where to update and what to update, right? So where to update is this, and what to update is captured by the tanh layer. So in terms of diagram, this is how it looks. So the new information is xt, and let's also use ht minus 1 from previous cell. Together concatenate them, pass through a sigmoid. If you are passing through a sigmoid, it's like a gate, right? So it's like controlling which information to add or delete. Now the tanh is going to create some candidate new information. So it's just a linear transformation of the nonlinearity. Okay, and this multiplication here, element-wise multiplication, is just removing some new information that's not needed, or leaving some new information that we think is needed, and then you do a element-wise addition. Okay, so that's the full operation. But in terms of these intermediate outputs, first is what is to be, what is new information. So it is a vector between 0 and 1. So is a vector where every coordinate is between 0 and 1, and c tilde t is the candidate new information. Okay, so given those two, you do an element-wise multiplication between them, and given those two, you do an element-wise multiplication, and then you add it on to your cell state. So add it on to, you forgot something, now you added new information, so you remembered something. That's how you interpret this LSTM architecture. Okay, so in the language model example, you add the gender of the new subject to the cell state. Okay, and so this replaces the old one that we're forgetting. Okay. Okay, so now we have forgotten something and we have added some information. Now what we have to do is to just now transform things so as to pass on, a new latent, new hidden vector ht, and a new, new hidden vector ht actually, and an output, which in this case is the same ht and ht. So so modification of cell state is these two steps, which I think I discussed before itself. You do an element-wise multiplication and addition of the modified c tilde t. Okay. So modified c tilde t is this, and element-wise multiplication of this forget gate is that. Okay. Now output. Output in this LSTM block is the same ht and ht. So output is just a transformed version of the cell state. So at this point itself, we have the cell state, right? So where I drew the arrow, we already have the CT, which is the cell state of this cell. Now we're just going to manipulate, somehow go from CT to HT so that it can be given as an output. Okay. So yeah, output is just a transformed version of the cell state. And how are we going to do that? Let's actually directly look at how we do that. So we again take ht minus 1 and xt to essentially create a gate. Okay, so this is again a output gate. So this gate, so we have the cell state. First, it's passed through not a neural network layer, but a simple tanh transformation. Okay, it's element-wise operation again. So cell state is a vector, right? It's a numbers between, it could be any number, it need not be 0 and 1. So you just do a transformation. So these numbers become between -1 and 1. That's what a tanh will do. And then you are multiplying that element-wise with this output gate. Okay, so output gate is again um, a neural network layer followed by a sigmoid operation. And then so this element-wise multiplication is producing your ht. Okay, so that's ht right here. Okay, so basically ht is just the output gate, which is again a vector between zeros and ones with elements being zeros and ones, and then a tanh transformation of the cell state. Okay, so that's it. So just think of it as additional nonlinearity to go from ht to ct to ht. Okay. So in the language model example, so since we saw a new subject, we may output information related to their actions, right? So if you think of language model, then we may have a higher probability that this new subject does something. Okay, so maybe there's higher weights on certain verbs and not high weights on irrelevant other words, which are like pronouns or something else. Okay, articles. So that's the summary of an LSTM architecture. It's basically you have forget operation first going on, then a remember intermediate computation that's being generated here. Then you modify the cell state with the forgetting and the addition of new information. And then once you get the cell state, you just modify that into a HT operation through a nonlinearity again. Okay, so those are the four, I guess, steps in this LSTM in each cell. So although it seems quite elaborate, it's actually not. You can actually do NN.LSTM, for example, to instantiate an LSTM block and use it in your, like neural network, class definitions. Any
Oh,
questions about LSTM?
so Professor, I mean, just how would it initiate? I mean, how would the first cell be? Because you don't have a prior
Yeah.
NPS.
So it's a good question for all sequential models, not just LSTMs. As you know, for example, LSTM, there has to be a C0 and H0, for example. Right? Let's say our indexing for the first for our sequences from 1. Okay, so if I pass X1, there is no H0, right? Or neither is the previous cell state. So in these cases, you can just default to 0, or you can add random numbers. But yeah, you can just default to 0 here. So
And
there's always going to be that edge effect that you will not have a previous input. Yeah.
yeah, and we build multiple hidden layers with this cell structures, right?
Yeah. So this just so we went into the depth of explicit LSTM block, but in the future we're just going to say, oh, here's an LSTM block, and it's going to produce a HT. Okay, we're not going to explicitly talk about cell state. So it's going to take, just like any other RNN, we're just going to say, oh, there's an XT, there's a HT minus 1, and there's going to be an output, which could be HT itself or whatever. Okay, so we're going to zoom out. And now at this point, there's going to be connected to another LSTM block, right? But the parameters will be the same. So if the parameters are W1, W2, W3, and W4 for the 4 neural network layers, it'll be the same weights. Okay, so all the weights are tied together. So if you're gonna, so let's say this is output T plus 1. Okay, now if you use this output for a loss function LT and another loss function LT plus 1, then loss with respect to these 4 matrices, for example, is what you would find as to I mean, the gradient is what you would find to update these weights.
Okay.
Okay, and again, same weights will be used for the next block as well. Same parameters.
Okay, got it.
Yeah.
Okay, it's clear.
I have a quick question. If we have missing values in the data, is it good enough to use zeros, to fill them with zeros to forget, or are there better methods to deal with missing values for LSTM?
So the data is basically, you're talking about XT, right? So I mean, because we're not controlling anything inside. I mean, everything inside is being controlled by these guys, XT and HT minus 1.
Right.
So when we start with the LS, okay.
Go ahead, please.
So I was just going to say that there was an earlier question about when we start with a single sentence, for example, the first word, let's say XT is I, right? I did, I went to UIC, or I did this or something, right? So when I pass the XT vector corresponding to I, let's say the word embedding that we got from earlier session, so we will not have HT minus 1 at that time, right? So at this time it's fine to pass all zeros, and I think that's what people do. Okay, but this is not really filling out missing data aspect, so I think in the larger, I guess, context, filling missing data is a whole field in itself, where sometimes zeros are appropriate, sometimes zeros are not appropriate. For example, when we did zero padding for images, zeros were reasonable, it was fine. Okay, but sometimes zeros are not the right choice. Okay, median values or something else could be the right choice.
I see. Thank you.
Yeah, and there is a whole field. So imputation or filling up missing values has its own considerations. Okay,
Right.
in general, yeah.
And is 10H common in RNN? Like ReLU is pretty much
Yeah.
conventional. Okay.
Yeah. So what we're describing here, vanilla RNN and this LSTM, TANH is common. Okay. So it's just that. So why is ReLU common with feed forward networks as well as with conv architectures, right? So it's just that it empirically performs well, and that along with a few other tricks lets you actually do gradient backprop nicely, so that you actually do a good because gradients can explode, right? I mean, we saw with sigmoid gradients can become zero, so you don't pass anything back and things like that. So empirically, it turns out that you can really get state-of-the-art numbers for many of the classification or other tasks with images or with CNNs and feed-forward networks there. With RNNs, it turns out that these are the choices, default choices. For the gates, it's sigmoid, and for the default non-linearity here for the new information generation, it happens to be TANH. You can change it, it's fine, but it just turns out that this is a good choice for RNN-based solutions. If you use RNNs as a basis for your sequence-to-sequence task.
Okay. Yeah.
Okay, and you don't have to actually use just RNNs as a basis for sequence tasks. Earlier, I wrote this word GPT-3. It doesn't use RNNs; it uses something else. Okay, we're going to discuss that at a later lecture. But it does. It's essentially a language model, so it actually also does a sequence modeling. So let's actually talk about very quickly. I mean, I'm not going to discuss too much here, but there's another, just to give an example, there's another RNN block called gated recurrent unit. So you might have heard or might not have heard. It's called GRU. Okay. So for example, there was a paper a couple of years ago which was it was for sequence modeling. In this case, they were looking at users' previous interaction on, let's say, something like Netflix, and trying to predict which movie they're gonna watch and engage with. Okay, so it's a recommendation system problem where you're looking at previous sequences of interactions and you're trying to predict what's the next likely thing that they'll interact with or buy or whatever. And there's an architecture called GRU for it. So just giving you a sense that GRU is another RNN block that's used not just with recommendations but also with NLP tasks. But there has again same types of blocks, but they're wired in a different way. A lesser number of gates here. You can see that there are only 2 gates. So there is a different interpretation for this block. Okay, so now let's now talk at the level of block level, because we've already got into the details of what's inside the block. But at the block level, it's just some parameters, right? Theta, 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 theta. The same parameters I used. That's good. So we just have, there's no explosion in the number of parameters. But now let's talk about a little bit higher at the block level, how the sequence models may look like. Okay. So once you have this input sequence, let's say x0 to xt, you don't have to directly convert this HT, maybe another linear transformation to output. You don't have to consider these guys as output, right? You can also actually stack them, stack 2 RNNs on top of each other. Okay, so 2 RNN unrolled diagrams for, let's say, for a given example, this x0 to xt on top of each other, and just think of this, instead of calling this so although I'm writing here x, you can just think of it as the h from here from the lower blocks is being passed on to the higher blocks. Okay, h, let me just call it lower and higher. I mean, just some names for these 2 levels. So the lower level hatches are again passed on as a sequence of inputs to the next higher level, where again there's an RNN unrolled diagram there. Okay, and then you can consider these as the outputs. So this is like stacking RNNs on top of each other. And you can do this not just for RNNs, right? Just like CNNs, you could play around with layers. You can permute the layers. You can have con, and then fully connected, and again a con layer, and so on. You can similarly, we are just playing around with these unrolled RNN diagrams. Okay. Same thing. You can have 3 layers. 3 layers, 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 3 and of course, I mean, you can say, oh, this, then the design space is too big. You can do 100 different things, and but there, I guess the tendency is to for the community is to mostly gravitate towards things which work well, really well empirically, and you kind of do slight variations on those empirically proven architectures. Okay. Um, so ideally, if you're applied, you're very applied, then you will not try to come up with the architecture from scratch. You will try to deviate, slightly from existing popular architectures. Okay. So, so that's a quick statement about RNNs, or at least how you'd use them in your application. So I'm going to talk about a lot of applications in a couple of minutes. So
So one question
yeah.
here. I mean, given that LSTM has a very good sophistication of remembering,
Yeah.
so is it like we always use LSTM over RNNs, or is there an advantage for RNNs to not remember so long?
Yeah. I think by default, if you, let's say you're spinning up PyTorch and you're trying to train a language model for your, let's say, small subtask for your, let's say, some domain. Let's say you're doing analyzing call center or contact center chat logs, and you're building your own recurrent network language model for that. Then you would just go with NN.LSTM block, for example, or GRU block. You will probably not go with the vanilla RNN that we discussed at the beginning. These just happen to be the popular ones that everybody uses.
Okay.
Okay.
Yeah.
Yeah, there's no there's no theoretical reasoning for one versus the other, because we're already doing a lot of complicated nonlinear computation. So it's kind of hard to say in theory which one dominates the other in any problem subclass. So empirically, these are the I guess the ones which have worked well in the past.
Okay.
And actually, you will see that RNN as these types of these types of function classes for sequence modelings have also now have a competition since at least 3 years, from the past 3 years. Slightly different architecture called transformer architecture, so which we'll try to cover at a later lecture. So so for the same problem, sequence modeling, you have RNNs, you have again transformers, and you can also use, for example, NN.transformer as a basic building block in your problem, sequential problem.
Okay, get it. Yeah.
So are transformers just different type of RNNs, or they are like totally different?
They're slightly different architectures. They don't explicitly look at the sequential. So this type of they don't have like an unrolled diagram, for example. So they have a different wiring connection and different underlying basis. Yeah. Okay. So they wouldn't be RNNs. They're a different class, but to approach the same problem, sequence to sequence modeling.
Okay.
Yeah. So I think this is not very useful. So what I want to spend time, I think we have only a couple of minutes, a few minutes left. So I want to talk about a few applications, and actually, so let me pick one of these examples, okay, so that you can spend time on one of them. So we start from this classification. Okay, this time I'll do image captioning, and next time I'm going to briefly, early part of next lecture, I'm going to talk about language translation, and in language translation, what I want to highlight is the notion of attention, and you'll see that attention is a basic idea even in transformers. So I'm going to spend some time on attention next time. So for now, I'm just going to give some examples, sequential examples without attention. And this is something that you guys can somewhat easily relate to, is the idea of image captioning. So in image captioning, the input is a single image and the output is a sequence of words. Okay, so it's input is fixed size, which is the image is fixed size, and the output is a variable length. Like for example, the caption could be of size 2, or caption could be of size 10 words. Right. So the way you're going to work is to use a pre-trained CNN as a feature extractor. Okay. What we saw in transfer learning section. So you have an image, you extract features, and that will be your H0. Okay. So instead of setting zeros, right? Recall this problem. our training example is an image and a sequence of words like straw hat. Okay, and end is just a token to say that you don't have to continue, right? Straw hat end. So given the image, you start with so you use that as h0, and then your current input is going to be straw. Okay, so this is a training time. Okay, so at training time, the current input is going to be start. Okay, at training time, given h0 and start, you want to predict straw. Okay, that's what is happening here. And then given straw, previous information, sorry, here, you have to predict hat. And given hat and previous information, sorry, not that, previous information, you predict end. Okay, so just to kind of expand on that, if you have a test, if you have a test image, first you generate the embedding, right? Just like before, just like we did in transfer learning part. Then that embedding will produce that plus your start token, some representation of the start token. So there'll be a vector corresponding to start token. Okay. If you don't have it, you can just start with some random numbers and learn that representation as well. That plus this is going to produce a hidden output h0, and that will give us a with some transformation of that will give us a y0. Okay. So yeah, so previous input plus current input, we're producing something now. All we change is that the RNN at the beginning has a input from a image. Okay, so that's just an additional thing. But other than that, once you move from there, the image part is gone. So you just have this. Okay, so in particular for test time, okay, at training time, you know what the sequence is, right? So you have straw. So your sequence is start, straw, hat, and you should produce end, hat, and straw. And one more input here is the image embedding, right? So image embedding. So this is the training time. So you know exactly what's the inputs and what's the output, and you can compute loss and you can update the parameters, right? At test time, you pass it, you get the image, test image, and you pass it through, and the start is just start, but you'll get a distribution, right? So you will produce a distribution over which word is the likely word to caption this image. Okay. From this distribution, you can actually sample or take the argmax if you want. You need to pick a choice. Okay, you can sample a word. If it happens to be straw, it's great. I mean, if straw is a true label, a true caption, but you could slightly have a different word, right? After you've trained your RNN, you sample from there, and then the sample is the one which is inserted when you compute the next output. Okay, and so on. So, and then in this test time operation, you want to hopefully sample end, okay, or you want to hopefully ensure that the score for end coordinate, that end token is the highest, and then you stop. Okay, so that's how you would do image captioning for a test image. So so that's image captioning. So it's quite straightforward. Detail for once you know how an RNN works. This part is the usual RNN operation. It's just that one additional input, which is the image itself. And surprisingly, this works and provides decent outputs. And of course, you can have many variations on top of it that have been proposed in the literature. So let me go to the next examples at the beginning of next class. Okay. Do you have any questions up to this point?
I have one quick question. Actually, I think the models you discussed, like RNN and LSTM, in all of them, we have labels, right? So they are kind of supervised learning. So in the real world data, when we don't have labels, but still we want to do this prediction in more unsupervised learning, how do we do that, and what are the potential models for doing that?
Yeah, so actually it's not, so for example, if you think of language model, it's actually not really labeled data, but it is supervised learning data because we are just predicting the next item. So for example, for language modeling, all you need is the data is a bunch of articles, like maybe you download the Wikipedia database, or you download like the Stack Overflow database, you have a bunch of answers and questions. So you don't have to have explicit labels in some of these tasks that you're doing. And you still will be fine because you're building a model which is just predicting the next item in your unsupervised data set because there are no explicit labels. Okay. But if you're asking about if you only have unsupervised data and you don't have labels at all, but you want to eventually create a supervised learning model, then you have to somehow get a proxy for the label, right? So either you can do the usual things like clustering and then post hoc interpret the clusters as labels in some sense, or something like that. So you have to collect labels if you want to ultimately produce a artifact, a ML artifact, which is going to be a predictor of a label, right? So let's discuss this aspect. Actually, we're going to discuss about unsupervised learning next time, some preliminary models. So maybe we can revisit this aspect of when in real world you may not have labels, then, but depends on what you want to do. You may have to collect data. But for language modeling, although there is no explicit labels, there actually labels are implicit because you're just predicting the next word, and the next word is the label, right? So in those types of problems, you're getting away with not really spending time on labeling.
Right, but I meant like kind of more like time series data than words. Then when you have a bunch of features, then it is not obvious what is the next feature, like at least to me. I don't know.
For time series, it's easy, right? So time series is predicting the next timestamp, so you don't have to explicitly label it, right? So but if you have a time series of measurements, then you just have to predict the next measurement. Even if your ultimate task is to not, so it depends. So maybe we can take it offline.
Yeah, sure.
Yeah. Yeah, thanks everyone. I'll see you guys next time.
Thank you.